Good morning, everyone. Welcome to the Texas A&M University Statistics Former Student Network webinar this morning. We're very fortunate to have with us today. I've already lost my notes. We have with us today Dr. You see, I lost my notes. Bandyopadhyay and Dr. He earned his.
Yes.
Thank you. I apologize. I told you I would not get it right. I didn't practice well enough. He earned his PhD in statistics in 2010 from Texas A&M University. And before joining the Colorado School of Mines, he was an assistant professor in the Department of Mathematics at Lehigh University. He's also been a visiting scientist at the Computational and Information Systems Laboratory at the National Center for Atmospheric Research, studying climate models. His core research approaches problems related to spatial and time series data. His expertise lies in developing novel inferential procedures under spatial and/or temporal dependence and investigating their asymptotic properties. His research has always been motivated by and applied to problems rising from practical situations in various areas such as climate science, environmental studies, finance, and biomedical studies, among others. He's an elected member of the International Statistical Institute and the recipient of the International Indian Statistical Association Young Statistical Scientist Award. So we welcome you to speak with us today and look forward to your talk. Take it away.
Thanks, Marcy. Can all of you hear me well, everyone? All right. Yeah, and you can see the screen, right? Everything is going fine. All right, good. I believe it's almost okay. It's 11, right? So it's still good morning in Texas. So good morning, everyone. It's 10 a.m. in the 10 a.m. at my place. Okay, so howdy. Okay, yeah, yeah, howdy. That's yeah. I have started to forget howdy because I haven't been to Texas for a long time, and I when I was a student there, and we used to greet each other with howdy, and so yeah, howdy everyone. So yeah, Marcy, thanks for the introduction, and I think that Marcy has already covered most of the stuff about me. So currently, I am an associate professor in the Department of Applied Statistics and Applied Mathematics and Statistics. So I started just before I start this talk. I would like to give a little bit into a few words about myself. So I graduated from Texas A&M in 2010, and my PhD advisor was Shoman Lahiri. So those of you know Shoman, you know that he is a very, very theoretical statistician, and my PhD thesis was all about theory of spatial statistics. I did a lot of theorems, lot of proofs, and all these things. And over the last 10, 15 years, initially I started as a theoretical statistician in my career, but over the uh, last few years, I have shifted completely to more applied or methodological statistics. So I still uh, I won't say that I don't do any theory right now, but more recently, my research is more driven by more interesting applied projects. So this is what I'm going to talk about today is basically one of those projects. And I mean, it's one of the most interesting projects I have ever worked on. So I'm going to talk about this, and let me just be very clear to you, this is not going to be a very technical talk because I thought that maybe sometimes when I was a grad student, I realized that when I was a grad student, I used to sit in the departmental colloquium, and if someone gives a very, very technical talk, sometime I used to lose the overall miss the overall idea or the interesting part of this problem. So I thought that maybe this talk you'll see that I'm going to skip a lot of details, But if you are interested to learn all of those details, all of these papers or the drafts are on archive, so you can always go back and check. And also, of course, you can always send me emails, and I can clarify if you have any question. You can always send me emails, and I would be happy to clarify. Okay, so with that, as you can see that today I'm going to talk about high resolution long-term weather data for energy. Now, before I start, I would like to give you a background of this project. So we all know that our future climate is uncertain. However, we know that years of observed climate and weather predict patterns and the development of several Earth system models, those allow us to project the future climate. Okay? Now, in terms of greenhouse gas emissions, it's so far I would say that the global surface or the change in the global surface temperature has been given the most publicity and attention. However, we all know, or the climate scientists know, or they anticipate that a variety of other atmospheric properties, for example, cloud properties or the aerosols, those are also going to be affected due to this climate change. But now the extent of this change is not certain to us, or it's uncertain. Um, so now, because of this change or this anticipated change in climate change, we can say that okay, the amount of incoming solar radiation at the surface of Earth is going to change, and that's going to, I mean, the PV industries, that's going to change the decisions made by the PV industries, the stakeholders in the next, let's say, 30 to 50 years, right? So now that's the background. NREL, this is a project supported by DOE, and especially this is a collaboration with National Renewable Energy Lab, which is located at Golden, very a few miles away from Colorado School of Mines. And I'm going to talk about the database that they develop and they maintain. But essentially, couple of years back, like say 3 to 4 years back, they came to us, the PI of that project at Envel. They came to me and they said that, okay, look, Shoti, we know that the solar radiation is going to change in the next 30 years or next 50 years, and we would like to project the solar radiation based on the changing climate. Can we do that? I said, yeah, of course we can do that. And it's a space-time problem, which I think I know a little bit about. So that's how this collaboration started. And once this collaboration started, we got to know a lot of things and a lot of details about this renewable energy stuff. So I'm going to skim through different concepts related to this project. But again, this is not going to be a very technical talk at all. Okay. All right, this is a joint work with my former PhD student. She graduated in June this year, and now currently she's a data scientist at Neptune Incorporated, and which is a local Colorado-based company. And as you can see that I have a list of collaborators from NREL, National Renewable Energy Lab, and this is also, I mean, I'm the PI of this project, but Doug Nitschke, who is currently the professor, and he is the co-PI of the project. So it's a collaborative effort of everyone. All right. This is a mandatory slide, I would say, that we all need to show that this is the funding acknowledgement. This whole project was funded by DOE, and this is in collaboration with NREL. Okay. All right. So I believe that I have already given you some background of this project or of this problem which I'm going to talk about. But essentially, let me just briefly summarize that NREL, the major contribution of NREL to the energy community is to build, they have already developed this, and to maintain a database called National Solar Radiation Database. Now, the private sectors, the stakeholders, the government, they always go to the NSRDB, this database, and they see that how, how the solar radiation is behaving in certain areas, and then based on that, they try to cite or look at the future solar facilities, right? Of course, I mean, you know that people would like to site the future solar facilities or the solar panels in a place where they can anticipate to get solar radiation at a constant or at an increased rate. So that's the idea. So they always go back to this database to uh, to make some inference about future solar radiation. However, as I said before, that the problem with this database is that they did not, this NSRDB, when they developed this database, they did not take into account the climate models, the output of the climate models. So essentially, they use some sort of physics model, a physical model to develop this database, but it did not take into account any sort of the climate change. All right. So that was the idea. They came to us and they said that, okay, we would like to revamp or develop this database for the next 30 to 50 years based on the climate, the changing climate patterns. And that was the whole point of this project. Okay? What are the other details about NSRDB? NSRDB is at 4 kilometer by 4 kilometer resolution, and so that's the spatial resolution, and the temporal component is from 1998 to 2014, and you can get it from hourly or 30-minute times. And as I just mentioned before, that typically they used a physical model for solar radiation at the surface and based on variety of the observations to create this Grigor data product. It's immensely useful. It's widely used among different private sectors, governments, other stakeholders. But the problem is that as we will or we might expect change in the solar radiation over the lifetime of the facility along with other changes to the climate system. So this is in blue because this is the whole purpose of this project. This is what we are trying to cover, or we would like to project the future solar radiation based on the changing climate system. All right. Now I'm going to get into a little bit of the statistical side of this project. Okay. Statistically, our goal would be, because we know that as a statistician, we really don't want to give one value for future, solar radiation at certain pixel, right? We would like to characterize the distribution, right, of solar radiation at the same space and time resolution as NSRTB under scenarios of climate change, right? So basically, we would like to give the the value of future solar radiation at pixel, as well as we would like to give some information that people can use to quantify the uncertainty. Okay. Now, how typically we do that? We do it using the method called statistical ensemble. Okay. Now, what is a statistical ensemble? I believe that many of you are already familiar with this term, but those of you who don't know what is a statistical ensemble, those are essentially equally likely set of representative cases that uh, that are samples from the distribution. Okay. So you can think about it's under the same scenario, what are the different samples we could get, right? In future. So if we know, let's say if I give you an ensemble of 15 members or 20 members, then you know that under this scenario, these 15 different possibilities can happen. And you can pixel wise, you can take the mean, you can take the standard deviation, and anything else and that would describe different statistics coming out of the distribution. Okay, that's a very empirical way of of defining or coming up with a distribution of a statistic, but this is widely used in climate science. Okay? The nice thing about these ensembles is that ensembles you do not need to generate and keep it. Okay, usually we or store it. Usually we use some sort of statistical emulator that builds those ensemble very quickly. So we typically what we would like to see or do is that we use these emulators to generate the ensembles on demand so that we do not have to store those ensembles, and that would reduce the computational complexity and the storage issue. Okay. Now I'm going to give you one small example of this ensemble members. What is the meaning of ensemble members? Now this is the data set I have got from this Heskey and Kipshirani's book on statistical learning, and it's this data is coming from Modified National Institute of Standards and Technology, which is the MNIST database. And you see that what I have done is that I have basically looked at the sample which contains the digit 6. Okay. And out of that, I have just looked at the first 20 members. So if you look at those at the bottom, the plot at the bottom, you can think of this as an ensemble of 20 members. And you see that all of them are showing you the digit 6, but all of them are slightly different from each other. Okay. Now, if I take the mean, and of course you can see that you have pixel-wise information. So if you take the mean of each pixel um, over these 20 members, then you will get the upper plot, the plot which we see at the top. And you see that this is a hazy plot. This is not as because it will have some uncertainty, so it is not as clear as each of those ensemble members, but still it is capturing the overall structure of the distribution. So this is the idea of having the mean of the distribution, how we can predict a value at a certain pixel based on certain certain number of ensemble members. Okay. Similarly, we can just take the standard deviation, we can calculate the quantiles pixel-wise, and you can talk about different statistics or distribution of different statistics based on those ensemble members. Okay. And as I mentioned before, that ensembles are useful to represent variation in complex objects. And that's how we typically do that. We just look at the value of certain statistics or standard deviation or this or that based on pixel-wise information. Okay. All right. Now I'm gradually going to get into the actual project, the actual problem, and before that, I need to define what is the response variable for this project. Okay. So as you can see that we have these solar panels here, and we get the solar radiation from different sources, and this plot actually or this figure actually describes that how we are getting these different things or different the solar radiation coming from different sources. So here in this project, our response variable is something called the global horizontal irradiance, and that's the GHI. And that is nothing but a linear combination of DHI, which is the diffuse horizontal irradiance, and some cos theta times DNI, which is the direct normal irradiance. And where this cos theta, the theta is the zenith angle. Okay. Now, the statistical problem here is that what will GHI look like in future years with a changing climate? So that's exactly what we are trying to solve in this project. Okay. Any questions so far for me? Okay. Someone saying me. Oh, what is DHI? DHI is diffuse horizontal irradiance. You see in the plot above, you see from sun, let's say we get into the cloud, the solar radiation that will be diffused through the cloud and some of the aerosols, and then it will come back to the solar panel. So that's the diffuse horizontal irradiance, and the direct normal irradiance is basically the solar radiation we are observing directly from the sun, or we are getting directly from the sun, but at a certain angle, right? That angle will be defined by the zenith angle. Okay. Okay. Yeah. All right. Now, what was the workflow for this whole project? Okay. So first of all, you need to understand, we all know that this NSRGB database was on 4 kilometer by 4 kilometer resolution, and it was on hourly or 30-minute scale. Now we would like to project the future solar radiation based on the RCM outputs, the regional climate model outputs. There is a problem here. The first problem is that, first of all, the RCMs are on a different resolution. They are usually, the spatial resolution is 20 kilometer by 20 kilometer, and the temporal resolution is daily, at a daily scale. Okay? So there is a mismatch between these two different types of resolution. So first we need to fix that. All right? The other thing is that even though the resolution is same, the orientation of the grids are different, right? So first we need to um, we need to consider all of these possibilities while doing the projection for future solar radiation. So these are a couple of things which we are going to do here. So first, we are going to regrid the daily GHI from the RCM on the native grid. By native grid, we mean the NSRGB grid. So NSRGBs are on 4 kilometer by 4 kilometer spatial grid. But first, I'm going to regrid the daily GHI from RCM to the 20 kilometer by 20 kilometer NSRGB grid. And then I'm going to run a multiple linear regression model with spatial correlation, temporal correlation, this and that. You all know how to do that. And I'm going to include a lot of other factors, for example, seasonality, elevation, and I'm going to build a model that's going to predict the observed GHI based on the NSRGB. Now, once we have the model, let's say we have the future solar radiation for the next 50 years or for the next 30 years, let's say. But those are at 20 kilometer by 20 kilometer spatial resolution and at a daily scale. But NREL wanted us to downscale that at 4 kilometer by 4 kilometer spatial resolution and at hourly scale. Okay, because they want that. I mean, so in the next step, we had to do the spatial downscaling, and we also had to do the temporal disaggregation. So what is the spatial downscaling? From 20 kilometer predicted value, we need to go to 4 kilometer by 4 kilometer spatial resolution. So that's the spatial downscaling. But the most important or most difficult part in this project was the temporal disaggregation part, where we had to go from the daily total. Basically, we have the daily total solar radiation for a particular for a for a pixel for a particular location over a day, and we have to disaggregate that into hourly scale so that the total is still going to give you the total daily solar radiation. Now, you can understand that during the temporal disaggregation, we can expect that it will follow the hourly solar radiation will follow a bell-shaped curve. So at night in the dawn, it's going to be very small. So it starts with a very small value, and then around noon, it's going to go up to the peak. It will take a peak, and then again it will go down. And in the evening or at dusk, it's almost going to be equal to zero. So it's basically going to give you a bell-shaped curve. And we are going to exploit that bell-shaped curve to predict the hourly or the disaggregate the daily radiation to hourly radiation. All right. So now this is the workflow, and I'm going to talk about three of these factors one by one. And again, without getting into too much details, but I'm just going to give you the overall idea um, how we took care of some of these components of this project. Okay, the first thing was the regrigging, okay, and prediction. So this is a plot that shows that the RCM, I don't remember which RCM we took. I believe this is coming from the WRF, so Weather Research Foundation. That's their grid, and that's the blue circle, and the target, the native grid, is the blue plus sign, right? Which is essentially the NSRTB database. And you can see that both of those are aggregate. Both of these are giving us two different grids, but their orientations are different. So we really have to do the regridding part first. Okay. So we tried different ways to do the regridding, and eventually we thought that okay, typically people use kriging, and we started with kriging, and we did the regridding at the first step using the usual kriging method. But here, Maggie one day came to us and she asked us a very important problem. And she said, the Soutir, we are doing this regridding, right? And then based on this regraded data set or regional climate model outputs, we are going to project or predict the future solar radiations at those NSRGB database. All looks fine, but we are not capturing, or we are not considering the regrading uncertainty in this whole project or in this whole step. We are just kriging to a new location. We are taking them as our new observations, and based on that, we are running a multiple linear regression model to build a model. But when we are doing this regrading, there are some uncertainties, and we are actually not considering that. So we should do that. And we say, yeah, of course. I mean, climate models, they typically do not consider this regrading uncertainty. But we thought that, okay, why don't we do that? I mean, let's do that, and let's see that if this regrading is, including or introducing some amount of uncertainty in our um, downstream, methods. Okay, the methods which we are going to apply to this data set later on. So first, this is I would like to show you a plot which shows that how this regridding can change some of the structure of the field. You see on the left-hand side, we have the values from a regional climate model grid, and the right-hand side, we just simply used kriging, and we regridded to the National Solar Radiation Database. And you see that, I mean, the overall structure is kind of same, but still there are some regions where you can still see some sort of discrepancy. Okay, so there definitely, due to this regridding, we are introducing some amount of uncertainty, and we all believe that yeah, let's see that whether these uncertainties are that important to consider. Okay. Um, so this is the framework. We regraded the data set. Now I'm going to tell you that how we have captured the uncertainty, or how we were trying to see whether this regrading has any significant effect on the downstream methods. Okay. So I'm going to start with a very simple model. Okay, the multiple linear regression model, and you see that on the left-hand side, so we have different RCMs, we have regraded, and on the left-hand side, we have NSRDB. On the right-hand side, we have these different RCMs, we have some other factors, seasonality, errors, and this and that. So the first method, the first approach we used is that we completely ignored the regrading uncertainty, and we thought that, okay, now we have done the regrading using kriging. So now this all of those values are on the same grid, 20 kilometer by 20 kilometer grid, and let's just build you know a multiple linear regression model. Let's look at the schematics of betas and let's see how things behave here. So we just use simple LM function to do that. And as you can see that here we are not considering any regression uncertainty. In the second step, we thought that, okay, now let's try to include some regression uncertainty here. How we can do that? If you look at this multiple linear regression model, and when we are thinking about the regregate data object or the data products, you see this RCM1, RCM2, RCM3, those are not fixed, right? Those are kind of, if you think about our linear model, y equal to x beta plus epsilon, where we say that, okay, this x is fixed. Here, we do not have x fixed, but we have x plus some epsilon, which is essentially coming from that regridding, right? So how can we take care of this? How can we implement or consider this uncertainty in this linear model? Okay. So what we did is very simple. First, we had those RCMs and we conditionally simulate each RCM onto NSRGB grid. And we looked at, I believe we looked at 100 different conditional samples at each of those pixel or each of those grid, right? Grid points, right? Um, Once we have a conditional sample, let's say that that's our field, that's our regraded data set, and based on that, we can run a Bayesian, very simple Bayesian inference technique. And we can say that, okay, for every simulation for a fixed surface of X, we can make several draws for betas and sigma square. And based on that, we calculated. So now we have 100 different conditional samples. For each of those conditional sample, we have 50 different, I guess we looked at 50 different draws for beta and sigma square. So we have around 500, sorry, 500 or 5,000, 5,000 draws of beta, right? And then we looked at the empirical distribution and we looked at the 95% confidence interval and as well as the credible interval. The confidence interval, when we were looking at the confidence interval, it was simply based on LM function. So we completely ignored everything. The credible interval is following the first 2 points here that where we conditionally simulate the RCM, and then for every simulation we use the Bayesian inference, the MCMC, to get several draws for beta and sigma square. So this is again, this is the model in a more statistical or in a more I would say that in a format that is more familiar to us, right? So I'm skipping that. And also in this whole project, instead of looking at GHI, we looked at the log transformed, a log linear transform data due to some reason. So I'm skipping that. But essentially, this is our response. X is our GHI value, but instead of looking at X, we looked at X star. Okay. But this is the overall conclusion. You see that I'm just going to show you the result for one single point here, this pink or you know, I believe this is pink. Yeah. So it's a point on the west coast, and you can see that we have the estimate of beta, right? The intercept, the beta 1 and beta 2. Um, for that point based on LM, and also we have the 95% confidence interval. We all know how to do that. And we also have this gray region, which is basically going to give you the histogram. This is the histogram of all of those 5,000 different draws or values of beta hat. And based on that, we also looked at the 95% credible interval. And you see that the credible interval, the 95% credible interval, and the 95% confidence interval without considering the rigging uncertainty, they are pretty same. I mean, there is some discrepancy. There are some discrepancies in the intercept, for the intercept, where the credible interval and the confidence interval are slightly different. But if you look at beta 1 and beta 2, which are kind of the effect of, the RCMs, the regregate RCMs, you see that they are pretty same. Okay. So what was the conclusion after that? Oh, let's just talk about the average bias and everything. So you also looked at the average bias, and this is basically by average bias we mean the estimate of beta coming from the linear model and the 5,000 different values of beta coming from the Bayes approach. Okay, so we looked at the difference and we look at the average over 5,000 different iterations. Okay, and you see, if you look at the average bias by location, you see that overall the bias is pretty small, right? I mean, it's not that significant. However, the nice or one thing to check here is that we could say that there is some sort of spatial structure is going on here. So we implemented, after that we did some spatial correlation or some spatial modeling of these betas, which I'm not going to talk about, but just to give you some idea like how this average bias will look like. We also looked at the adjusted R square and the coverage. Okay, this adjusted R square, we all know that it is out of sample prediction. So basically, it's not. It is going to tell us that whether we are doing any overfitting or not. And you can see that the adjusted R square values are pretty good. We have some low values along the coastline, but it's always the case. I mean, this is the California. This is some of the pixels around along the coastline, and predicting something along the coastline because of this non-stationary and everything, it's always a tough problem. And it's not here. It's almost in all problems where you are trying to predict something at that junction, at the boundary, it's always a huge problem. If you look at the coverage in the month of May, you see that the coverage is also, in between 91% to 95%, so which is telling us that our method is kind of doing pretty well. Okay. So what's the summary of this rigging step? So we make the conclusion after doing all this that the RCM output is not on the same grid as the NSRTB product, and we know that rigging uncertainty is an often ignored issue in climate science. However, even though we deliberately did this Bayesian inference, or we followed this Bayesian technique, this rigging process does not appear to inflect the uncertainty. Okay, so that was our final conclusion, at least for this project. That was our conclusion. But if we have a different data set, it is possible that we will come up with a different conclusion. Okay, this paper got published, I guess it was early this year. It got published in the journal ASCMO. Okay, so again, this is also an archive, and if you would like to know more about this rigging uncertainty, how we did all the details or took care of all the details, you can go to the actual journal article or you can look at it on archive. The next step is bias correction. So I'm going to go over the bias correction pretty quickly because it's more for the climate scientists. This is proven or well-known fact that whenever we are trying to use any climate models to predict some other climate variables for future, in future, there is always some sort of systematic bias present in that projection. Okay, and people use different types of bias correction. Some of the well-known or very popular methods are something called quantile mapping, or some people use delta method. Delta method is more, it's more ad hoc, whereas we thought that this quantile mapping is has some statistical background. So we decided to use quantile mapping to adjust the quantiles of the model distribution to match to those of the observed distribution. So I'm skipping this part. I'm not going to get into too much details because I think I have spent too much time on this regrading step. I would also like to talk a little bit about this temporal and spatial downscaling part. But essentially, we did some bias correction after fitting this multiple linear regression model using this quantile mapping. Okay, and this paper currently it is under revision at Solar Energy, and I need to submit. I mean, Maggie has done something, all of those um, uh, for the revision, and we are planning to submit this revised version to Solar Energy within a week or two. So that's the current status. Now that's the last piece. So now we have projected NSRDB database at 20 kilometer by 20 kilometer spatial resolution and at a daily scale. Now the final step is to do the spatial downscaling. So from 20 kilometer by 20 kilometer, we need to go down to 4 kilometer by 4 kilometer by 4 kilometer. And also from daily, we need to go to hourly scale. So these are the two things we need to do. Now, first, I need to show you some, how this whole thing behaves, right? So I have taken three different points over US. So one is the purple, dark purple, which I guess is which is on the western coast. We have taken a blue point that's in the Midwest, and we have taken a green value or green point that's on the east coast. So our NL scientists they say that depending on the topography of the regions, we might get different types of um, solar radiation. So we need to consider these three different regions separately. So that's what we did. Okay. And if we look at, let's say, you see that for each of these points, we have this time series data. We can see that this is the spatial points are fixed, and we are looking at three different time series, right? What are the major observations? We see that noise can occur throughout the day or only in AM or PM. So ideally, if you look at this PDF, you see that dotted line, that's the ideal. That's what we would like to get. But due to cloud patterns and all those, aerosol properties and all those things, we never see that, right? We see a damped version of this, that's we call, the dotted lines are called the clear sky GHI. That means that's the oracle. That's what we would like to see. But sometimes in the sunny day, we get that. But in many days, when we have clouds or rainy day, we don't see that. But overall, you see that it has this cyclical pattern. So it starts at zero, it goes up, and it attains a peak around noon, and then it goes down. Okay. And also we looked at some of the clear sky days, and we see that these clear sky days have no extra noise. And you can see that some of those purple lines or blue lines, they actually are very similar to the dotted line. So that means that on those lines, on those days, we did not have any. Those were very sunny. So we got very good solar radiation, and the amount we expected, we got that. Okay. All right, so this is the final step, and what is our goal? First of all, you need to remember that this is a joint project with NREL, and NREL is going to explain it to other scientists, stakeholders. So we have to create a very, very simple, explainable, efficient algorithm. We can always, I mean, when I gave this talk to other places, so many people they came to me and they asked me that, okay, why didn't you use this or that or this or that? I mean, all of those nice ideas. I said, yeah, absolutely. Those are all very nice ideas, but remember that at some point we need to explain everything to non-statisticians, right? To scientists who are going to take our data or take our data product, and they are going to do something. Um, they are going to do something important based on that data product. So we need to keep it very simple. Okay. The second point is that we need to align our hourly data with number of clear sky hours and amount of daily variability. All right. And finally, we need to incorporate spatially and temporally correlated cloud patterns. We all know that if Denver is cloudy, then we can expect that, okay, maybe Colorado Springs or Golden or Boulder, we will also have some spatial correlation, and we can also expect that all of those neighborhood places are also, they are also going to be cloudy on that particular day. So somehow we need to incorporate this information into our downscale data product. Okay. Now, first, I'm going to talk about the temporal downscaling or temporal disaggregation. The idea is very simple. What we did is that for a particular location, okay, when we looked at, we saw that the temporal, it follows certain diagonal patterns. So we started with a parametric model. Okay, this a semi-parametric model, I would say. So you see that this is the semi-parametric model, and it has different parameters involved, and which we are going to estimate all of those different parameters using nonlinear least squares. But I'm not going to talk much about that. But most precisely, if you look at these three parameters, I would like to say that these are the three crucial parameters which is defining the diagonal pattern. The first one is the beta. So beta is the shift for time of peak clear sky GHI. So we cannot expect the peak to happen every day at 12, right? Some day it will happen at 11:55, some day it will happen at 12:07. So the peak is a random quantity, right? And this beta parameter is going to decide, or it's going to tell us that when this peak is going to happen. Tau is the width of the profile or the length of the gay. The length of the gay is not same, right? It's going to be different for different gays. And alpha is the daily total GHI, and that's also not going to be the same, right? We can expect the alpha to be the same over different gays, but different gay we are going to get different um, total GHI based on some other phenomena, right? So this alpha value is also a random quantity, and we need to estimate those parameters or those things based on using some nonlinear least squares. So that's what we did, and based on that, let's say for a particular location, we looked at the GHI for in October for a few days, and you see that it is capturing the overall pattern of this diagonal pattern pretty well. This is the observed one, and that's the adjusted template. Now, what's missing here? The missing component is the small variations, right? Now we got the overall idea that, okay, we can now model the mean response pretty well, but we still have to model, or we need to take care of the small variations here and there. So how did we do that? Very simple. We looked at the principal component analysis. So this is what we did. Essentially, we looked at the residuals, right? We had this observed, we had this, the mean diagonal template. And based on that, we calculated the residual matrices. And then based on those residual matrices, we looked at the principal components, or sometimes we call them the empirical orthogonal functions in spatial statistics or spatiotemporal statistics. And we saw that if you look at this proportion of variation explained plot, you see that up to 4 basis or principal components, we are capturing almost 80% of the total variability. So we thought that, okay, that's pretty reasonable. So let's just stick to 4 different basis functions, okay, or 4 principal components. These are some other plots related to 4 different basis functions, and it basically shows that how the overall structure of the curve will change depending on addition of these basis functions. In particular, I would like you to look at the third plot, where I have started with the adjusted template, which is the overall, with no variation. We have the template, and then I gradually added one basis function, two basis function, three basis function, and four basis functions. The final one is this black one, which looks, you see that it has this diagonal template or the diagonal pattern, but at the same time, it shows us some variation, which is very, similar to what we typically observe on a particular day. All right. So we did that for two different locations. One is on the West Coast and one is in the Midwest. And you see on the top panel, this is coming from the West Coast location, and we have U1 four different basis functions. I'm sorry, four different U's. So uj, if you look at this equation, you see that j equal to 1 to up to 4. So we have, and these phi j's are fixed. Essentially, those are the basis functions. So we looked at the coefficients, right? And those are the weights essentially. And we looked at the plots of those weights. So the upper panel gives you the plots of U1, U2, U3, and U4 for a particular point or for a particular region in the West Coast, and the lower panel gives you the same, the U1, U2, U3, U4, the plot of those coefficients in a certain region in Midwest. So clearly, if you look at this UIs, the plots, it shows us a lot of spatial correlation present in this data set, right? So that clearly, so in the next step, we did some sort of spatial modeling on this U coefficients, and we came up with certain smooth surface for these U coefficients, which we could use to do disaggregation or downscaling, spatial downscaling. Based on that, based on everything, whatever we did, this is kind of a simulated cloud patterns. And you see that these are looking, I mean, when we compare them with the actual database, I mean, the data set, they look pretty reasonable to us. Okay? And we also looked at different metrics. We looked at holdout sample, we calculated different metrics, and those are pretty nice. I mean, those are pretty small. These are simulated clear sky days, and we also looked at the simulated time series. Here we have looked at two different locations, A and B, and you see that these are kind of two different examples for those two locations for the temporal, for the simulated time series, which seems to be very reasonable, and this is very similar to what the NSRGB database or the NSRGB observations look like. All right. So this is my conclusion. So basically, we successfully downscaled daily average GHI to hourly average GHI. We also implemented some method that simulates spatially correlated cloud patterns. We also looked at different metrics, as I mentioned before. We looked at number of clear sky days. We looked at something called variability index, and those are the metrics. I mean, the annual scientists, they wanted us to check that to see whether our projection or our prediction is reasonable or not. And I believe that it's almost final and at its final stage. So it is being implemented for the entire CONUS, and NWEL is coming up with a database that's called NCDC, National Climate um, NCDB, National Climate Database. So I knew that it's going to come up in October. So maybe in the next few weeks, they are going to come up with this entire database with a new website. And feel free to give it a look. And if you have any question, you can always reach out to me, and I will be happy to answer any questions related to this. So with that, I'm going to stop here. I think that that's pretty much all I have for today. Thanks.
Great. Thank you, Dr. Bandyopadhyay. A very interesting example of using statistics in a real world problem with the climate. Does anyone in the audience have any more specific questions you'd like, or any questions, I guess, that you'd like to ask our speaker? We have a few minutes.
Okay, someone asked me what are the RCM1, RCM2, and RCM3? That's a good question. RCM1 and RCM2, those are Canadian Regional Climate Model, version 4 and version 5, and RCM3 is the WRF. So we looked at all possible RCMs, but we saw that, doing some variable selection or, simple techniques, using some simple techniques, we saw that only these three RCMs are really important and significant in projecting solar radiation. So we stick to these three RCMs for our entire modeling. Okay, so Canadian RCMs, version 4, version 5, and WRF. These are the three.
It looks like there's a comment from Joe Sweet. He had not taken any spatial statistics coursework. Can you
I yeah,
recommend a
all right,
book or
sure.
article?
Yeah, absolutely. That's a good question, and that gives me an opportunity to advertise a forthcoming book that me, Will Kleiber from CU Boulder, and Gagnitska, we are writing a spatial textbook. Hopefully, this is at a very final stage, and we are talking with Springer, so hopefully it will be coming out in next few months. But so far, I mean, when I was a grad student, I looked into two different books. The first one, a book drop. What? Okay, I don't understand what is that. What is the meaning of book drop? But yeah, what's that? What is book drop? Oh,
Uh,
okay, all right, an advertisement by the author. Yeah, but Joe, just to let you know that you can look at Noel Cressy's book. And there was another book. I looked at Noel Cressy's book quite a bit. And more recently, there is a book by Noel Cressy, Chris Weichel. They came up with a book for spatial, I think spatial temporal data set. So that's another book you should look at.
there was another question on a programming language that you might have used for the project.
What programming language was used for the project? So Maggie used R primarily. So our in this project, as you can see, that first we wanted to develop the model for a small region, for a small data set, and then we gave it to Enrel, and they had their HPC team. They converted our R script to Python, and then they did everything in their HPC. But whatever Maggie did, that was all based on R. And personally speaking, I don't know much about Python. And if I always tell my students that look, if feel free to do everything in Python, but always remember that if you get into any trouble, I won't be there to help you in debugging because I don't know much about Python. But if you have any problem, any issues with your R script, I can look at it and I can help you debugging that code. But many of my students nowadays, they have started to use Python and tidyverse, dplyr. I'm still an old school person. I am a base R person. I have little knowledge of Python, but not a lot. But I always get a bunch of smart students who do all these things, who take care of this, so I do not have to worry too much about these things. Thank you. Any other question? All right. I
All
believe,
right.
yeah.
Awesome talk. Finished up just within
So,
the hour.
Marcy, I have quick question. Um have we recorded this talk or
Yes. Yes, it's being recorded.
okay.
And with your permission, of course, it be placed on the
Fine. I
SFSN
think I
web.
have already shared my permission, so it should be fine.
Okay.
Okay. No,
Yeah.
I just wanted to know. Yeah. Thank you.
Yeah, no,
I just
perfect.
send me the link. Once you have the link, please send me the link. Okay?
Perfect.
Thank you.
Absolutely.
All right.
Well, thank you. Thank
Nice
you
to
very
talk.
much.
Thank you very much. Yeah, nice to talk to you. All
Yes.
right. Thank you.
Thank you,
Bye-bye.
everyone. Take care.